Hi folks, we are starting with our next talk, Missing the Apex, predicting F1 races with Python. Please give a warm welcome to Josh.
Good morning, everyone. So like I said, just introduced, I'm Josh Weissbock, and we're gonna be talking about F1 and how we use Python to do some basic analysis with F1 races. So for those who aren't familiar with F1 or motorsport, the apex is just the fastest line through the corner. If you don't take the proper line, you won't achieve maximum speed, and you'll end up being behind. So when you miss the apex, you probably made a mistake. So the goal of this presentation is to walk you through a story and a scenario of how I use Python to work on an academic paper that was inspired by another academic paper, how I use Python to collect data, to wrangle data, and how to do some analysis with this, and really to inspire you to show you how you can use Python, just simple Python, to do basic work that adds to the academic world, as well as just get involved in sports stats. So I'll give you a quick introduction of F1 if you're not familiar with what the sport is. I'll talk about the motivation of what got me into this problem specifically, and then we'll start talking to some Python specifics. We'll talk about scraping, we'll talk about data wrangling, we'll talk about analysis and the results I've achieved, and then what's next. So short introduction, I'm Josh Weissbock. I've been Pythonista since 2006 when I was introduced to it in undergrad, back in version 2.4. Took me a good couple of years to switch over to 3 to upgrade all my projects through the 2010s. This is my 5th PyCon. My first one was in Montreal in 2014, 2015. Went to both Salt Lakes, and then this is my 3rd one. And this is my 5th one. So this is actually my 3rd talk at PyCon. I've spoken before on web scraping, so I have much more detailed talks on that, where I talk about things related to distributed scraping, bot detection, etc. So you can always just search my name if that kind of topic interests you. As well as last year I talked about how I worked with an NGO using ML to help my local community. So I'm currently a PhD student up in Canada, in Ottawa, Canada, at Carleton University, where I'm working in the data science department. My background is computer science with a bachelor's and master's in computer science. I finished my master's over a decade ago, where I was using machine learning to do basic hockey statistics and basic hockey predictions. And that's gotten me into the industry where I've been involved in talent identification within sport. So the idea of, can we look at U18 athletes who aren't even adults yet, and try and predict them in their sport at their elite level. And that's what I'm trying to do with my thesis right now. Using current data science approaches and ML approaches with traditional sports data, such as performance data, psychological data, combine data, and qualitative data to try and make predictions on these players. So I've been involved in sports for the last 15 years, public and privately, working with teams, doing all kinds of data type roles, data engineering, research and development, performance analytics, and analysis for the team decision makers. And all of these have intertwined with Python. So let's start off and talk about what is F1 if you're not familiar with the sport. So F1 itself is a motorsport. It's the pinnacle of motorsports, the fastest, most prestigious form of auto race in the world. It's an open wheel single-seater series, which means that all cars have exposed wheels and exposed drivers. All the cars are custom built, so it's not a spec series. NASCAR is an example of a spec series where almost every car is the same, where F1 is entirely built up from the ground up. In the league, there's multiple teams. Every team has 2 drivers, and they enter races, earning points. And because the way the sport has developed over the years, performance more or less has hit a point where almost everyone is performing fairly similar. So these tiny margins matter. The difference of 1/100 of a second can make the difference between first and second. And that can come down to everything from driver skill to just simple aerodynamic differences in cars. F1 in a single year, the season is focused over a single year. They race from March through December with 20 to 25 races in a year, called Grand Prix. Typically they happen every second weekend. There's actually one happening this weekend. They race all around the world. Countries in green are the countries where they currently have races. Countries in red are where they have had races. And during the year, like I said, there's multiple teams. Right now there's 10. Every team has 2 drivers, and they're racing for points. You earn points by your finishing at the end of the race. The better you finish, the more points you get. If you finish first, you get 25 points. Second, you get 18. Third, you get 15. All the way down to 10th, where you get 1. And why that matters is for the individual drivers, the driver with the most points at the end of the year is crowned the driver championship, which is more important for marketing and probably fans. More important to the team is the constructors championship, which is the team championship, and it's the amalgamation of all the points that they collected from all their drivers in that year. And why that matters is because money. You end up getting more money for a team the higher you finish. And with more recent changes to try and bring lower costs for teams, there's also resource limitations. So the higher or lower you finish in the year, the more computational CFD time you get, more wind tunnel time you get. There's benefits for trying to finish first. So yeah, in a single weekend, the pressure's on. You need to get points at every single race. So in a normal weekend, the structure is as follows. Like I said, there's a race on this weekend in Emilia-Romagna, which is in northern Italy, near San Marino. And this is the typical structure of an F1 weekend. You have race sessions over 3 days. Friday, Saturday, Sunday. This has changed over time, but this is the general pattern. Friday, we'll see 2 practice sessions. Saturday, we'll see a practice and a qualification. And then Sunday will be the actual race. Practice sessions are an hour to an hour and a half long. They're free-flowing. There's no limit on when you can go out, what you can do. Teams use it for all sorts of data collection because they don't have much external testing time. They use it to test different setups for their cars in preparation for the race. They also try out rookie drivers. It's one of the few times they have to actually try 2 new people. All this leads up to qualification on Saturday, which in its simplest explanation is a 3-round time trial where every round the bottom third of cars are eliminated, the slowest third of cars. And what happens is the final results from the qualification, you'll have an order from fastest to slowest, become your starting grid on the next day. So fastest on qualification starts at the front the next day. And that's important because passing is overtaking is hard, and clean air is key with the aerodynamic rules. There's a little caveat there where it's not a one-to-one correlation because penalties can be applied to qualification results. So you can finish first but start a little bit backwards. For example, if you broke a rule or if you use more components than you're allowed in the year. One thing to highlight is sprints do exist. Sprints are a newer form of racing. They're introduced in 2021. They're basically a mini race on the Saturday, and they change the weekend completely. And more or less, I've ignored these for this analysis just because they're so new and so limited. So that's basic F1, and I'll explain what motivated me to get me into this problem. So again, working on my thesis, working on my PhD, going through sports-related papers, and I came across this paper called Relationship Between Starting and Finishing Position in Formula One Race Cars, published in 2017 in the International Journal of Performance Analysis in Sport. And as I read it, I'm like, how did this paper get published? It was a simple correlation between the starting grid and the finishing grid, and that was it. There's no digging deeper into the rest of the weekend. There's no dealing with weather, penalties. There's no dealing with the evolution of the car over the practice sessions. It just said if you started first, you're going to finish first, which is pretty obvious and didn't really lacked a lot of depth. So that really motivated me to get into this problem space. And as I read it more, it lacked a lot of details. So like I said, it treated starting position independent from qualification. The paper was only based on 4 seasons, small sample size. They looked at 2006 to 2009. I'm not sure why they limited to such a small number. I know the analysis was done around 2010, so I can assume why it stopped in 2009, but I couldn't figure out why it only went to 2006. So really, it only had 70 races of data. And the thing that really bothered me was they only looked at the top 8 drivers in the race. If you're looking at the evolution of a race, you'd want to look at every driver. And at the time, there's over 20 per race. My hypothesis is that they're just looking at those drivers who actually earn points, because pre-2009, the top 8 drivers only got points instead of the top 10. But still, you need to be looking at the entire data set. So all this really inspired me to get into this problem. So I set hypotheses. What can I test with data? What can I use Python for data? What can I do to look at this problem? And I really want to know, can I look at the evolution of the weekend as a whole? Can I look at all the practice and qualification results to try and see how they impact the final, the race day results? So the first thing I need to do is get some data. I was very fortunate with this problem that the data sources were very, very clean. If you go to Formula1.com, they have basically all of the historical data for all their races. It's nice and easily organized by season, by race, by session. Every single page is unique where it only holds one table of data. And as I look at the different URLs, it's very easy to start paginating through them. Just by replacing the URL, the season, the race name, etc., it was easy to start rotating through these. And it also provided a lot of detailed data that could be used for a lot of different projects. So we had things like the position, driver, team, lap times, gap times, points, sector times, gaps off leader, etc. So this isn't an AI API, it's just the website itself. And so this talk isn't super deep into scraping, but I'm going to touch on a couple little points I picked up that I highlight that are useful in any scraping project. And one is when I started inspecting the HTML of this website. Again, not expecting to start reading through all the code, but what to highlight is the table of data itself was a very clean, well-presented HTML table, which means I could target it very easily using basic Python packages. It also used CSS selectors, so it made it very easy to identify. And the website itself was also very statically generated, which meant that I didn't have to use anything fancy like Selenium to deal with auto or dynamic content. So right away I knew I'd be able to use something like beautiful soup, requests, extract that table, throw it into I use pandas preferably to throw into a CSV. And then from there, I knew this is probably the easiest scraping, cleanest project I could come up with. And that's basically what I did. I created a simple process to run through all the seasons, all the races, all the sessions, rotating through those different options. Go through all the years, go through all the races. On the main season page, it has a list of all the race IDs and race names. So for example, Australia would be an example with a 4-digit code. You plug those in, rotate through, extract the table, and save it to a CSV. So from the Python specific side, there's a number of packages that end up being very useful in this, and these are pretty standard for any scraping process. Request to fetch the HTML resource, beautiful soup to be able to parse through it. I prefer pandas for a lot of things, including taking that HTML table and turning it into a CSV. I'm sure there's other ways to do it or better practices, but that's just the simplest way for me. One thing I learned in this process was that read HTML under pandas requires a certain file type, and the beautiful soup tags don't match that. So I had to use IO string IO in order to convert between the two as just a quick bridge. And then I started getting some tools that are always useful in any type of scraping problem. One of the biggest things issues that happens in scraping is networks fail. Networks get wonky, networks get weird. And one of the biggest ways to fix it is just try again. So retry is a great package where you can wrap any function with it, tell it to wait 2-3 seconds, back off multiple times, and just retry if it fails. I use the OS package just for managing the files that I was scraping to. And time I always went for some basic bot protection. So like I said, this became a very lightweight, single pass scraper. This is not something I'm hesitating to productionize, just something I was going to manually run so I could collect the data. Once I had it, I never need to use it again. Like I said, I put some basic bot detection in there, such as the random random delays of time between every request, just so you're not hammering the websites, as well as just adding basic headers to the request so it doesn't get flagged as an obvious spot. All of the data was saved locally to a CSV, and before every request, I would check if the data had been scraped, just to save that request time. And again, all this was not meant to be productionized. Again, if you're interested in scraping, just look at my name on YouTube. I've talked about this at PyCon before in a much more detailed way. Now, of course, there's always edge cases that come up, and there's some interesting specific ones with F1. So like I said, almost all the pages were clean and easy to scrape, very standard HTML. But what happened was there was a couple races that would have a result page, but nothing would generate. And that was because of real-world events. So the two that really popped up in my period, so just highlighting, I was scraping from 2006 to match the original paper to 2023, because when I started this in 24, it was the last complete season. And in that time, there's two races. There's the 2023 Emilia-Romagna Grand Prix, which was canceled due to massive flooding, and that's a picture at the top. And in 2017, the Chinese Grand Prix had such bad weather that the helicopters couldn't fly. And just due to safety, they need to get the drivers between the accident and the hospital in a short amount of time. So they weren't able to run those sessions. So I just had to figure out what these issues were, investigate if they were race issues, programming issues, or real-world issues with the website, and simply just add in the logic to skip these. Given that I was manually running this, that I was checking resources, if the website was already, the session was already scraped, it became very easy to restart. So as a result, I ended up getting 3 CSVs of all the data from all that time. These cover all the sessions, the practice sessions, the qualification sessions, and the race results, and it's pretty straightforward. But it's great that I have the data, but it's not really useful at this stage. So next I had to actually make it useful. So the goal ultimately was to take all those CSVs and get them to something much more workable. I wanted to pivot it so that every row would be one driver for one race with their full weekend's worth of results. That way I could quickly run something, say, a correlation between columns would be much easier. So I need to pivot, merge, clean. Pretty standard problems within data wrangling. Again, this wasn't productionized, just ran it in a Python notebook, and this was almost all done in pandas. First step was dealing with your normal data cleaning issues. There's a number of random artifacts from, that would show up as blank columns in the table. And those just came from the visuals on the website where they'd have blank table columns. So I had to get rid of those. Did a lot of normalization of name sessions for simplicity. Also because I didn't want to keep typing out the full names every single time. So for example, changing practice 1 just to P1, and then appending those to the different sessions. So instead of gap or laps, you'd have gaps P1, laps P1. So you know it would be the laps and gaps for that particular session. Then you dealt with the standard issues of filling in the blanks, filling the missing gaps, dealing with DNS handling, which is not domain name service. It's did not start, so drivers didn't even start in the session at all. And again, cleaning with some name mismanagement. So for example, in some columns they call it Toro Rosso Ferrari, but in other columns they call it Toro Rosso dash Ferrari. So just again, making sure it's all standardized. And again, the edge cases popped up. Same as the ones that we talked about when scraping. There was a number of sessions that existed that were able to be scraped, but weren't able to be showing up in the data, which again were all weather related. 2015 US Grand Prix, 2019 Suzuka, 2020 Germany, Syria, Emilia-Romagna, and 2021 Russia all had sessions canceled due to weather. They'd show up in the data, so you'd have to remove them because you weren't having complete sessions. Again, touching back into the sprints, they were scraped because, again, the website was pretty standard. I had to remove them from the data because, again, for this project, I wasn't using sprint data. And to do that, I had to manually identify which sessions which were involved. There's only 3 races in 2021 and 2022, which made it easy. 2023, they evolved to having an extra qualification sprint-related session. So again, it was 6 sessions to deal with. So again, standard wrangling, and what that gave me is a full data set of every driver and all their sessions from 2006 to 2023. So this is on my GitHub. If anyone wants to do any Python work, you can just grab it and start your own F1 project. It's a pretty complete data set. Again, it's 2006 to 2023. It's over 7,800 driver race entries over this time. So it's not just those top 8 that I had a problem with, but everyone. And it even included the drivers who only raced part of a weekend. So now I had the data, it was actually time to do some analysis, the actual piece that we want to get into. All the work to do just a little bit of stats. So the first thing I need to do is establish a baseline. I want to take what the original paper did and replicate it, just to establish a baseline that I was getting the same results to them. So I took the clean data. I only kept the 2006, 2009 initially, kept the same top 8 drivers, just again to make sure that, that I was matching their data. And with that, I also dropped all drivers who didn't complete a full session. So for example, if a rookie driver showed up and they only did the first practice but didn't do the rest of the weekend, obviously I wasn't going to include them in the data. Same as if someone was sick and missed the second or third practice, I'd drop them, because I want to see a driver who was consistent through the entire weekend, through every session. So the first analysis I did was I used a contingency coefficient, which measures the association between 2 categorical variables. In this case, those categorical variables are the starting grid position and final race positions. And I did that specifically because that's what the original paper did, and I wanted to replicate what that did. And that was super easy to do in Python. Pandas has the crosstab function, where SciPy has the chi-squared contingency function. So with that, I was able to establish a baseline that matched theirs, 0.63. I also then just quickly expanded it to the top 20. The same years, 2006, 2009, top 20 race start and finish. And I saw a huge jump in the C value, going up from 0.63 to 0.76, which showed an even stronger association before, which started leading to my hypotheses. Like, the original analysis was incomplete, and there are more strong associations within the weekend than just what they had presented. So I want to start looking at all these sessions. I looked at, again, using contingency coefficients. I added Spearman's row, which measures the rank correlation instead of checking just association between the categories. And again, this was easy to do in Python. SciPy offers the Spearman row function. The one thing I did do at this stage was I switched, instead of 2006 to 2009, I switched from to 2010 to 2023. The reason starting at 2010 was because that was a major technical change in regulations, and I wanted to ensure as much consistency as possible instead of just catching the end of a year of one. I want to look at all the sessions and how they evolved and how they correlated with the final results. So the starting positions, the qualifications, the practice sessions. And the big takeaway, not expecting everyone to start reading and analyzing that table, is that both the C value and the rho value and the relative frequency, and the relative frequency is just how often when you start in a position you stay in that position. All of these suggested that the qualification was the strongest indicator of prediction of success on the weekend, which makes sense. If you're the fastest car in the time trial on the Saturday, you're probably the fastest car on the Sunday when you're racing. It was also interesting to see that the evolution of the practices had some signal. Practice 3 was the strongest of the 3, practice 2, and then practice 1, which again makes sense with the sport. Throughout the weekend, you're getting ready to race, so you're using those sessions to prepare. So it's figuring out the small little issues. So just a quick heat map, which was this is done in Seaborn in Matplotlib. Just taking that data, showing the relationship between starting qualification position and finishing position. And you can see there's a strong diagonal trend, way stronger in the top corner, where if you're up front, you're probably gonna finish up front. It fades in the middle a bit, which is, I'd say, a bit more representative of the sport. There's a bit more chaos in the midfield, where cars are a bit more equal. There's more opportunities with error, with strategy to pass. And the bottom kind of fades out as well, which also kind of reflects that cars ahead of you tend to not finish, so you have the opportunity to move forward. Quick little analysis. I was curious about looking at the contingency coefficient, the Spearman row, and relative frequency between the eras. I targeted 2006, 2008, which is when they used the V10 engines. 2009 to 2013 were these V8 engines, and KERS, which is the kinetic energy recovery system, where you store braking energy as battery energy, which gives you extra energy in the form of boost. And then 2014 to 2020, which is the turbo hybrid engine era. Big takeaway from that was that as we got closer to the current day, all of these became more and more stable and more predictive. And I think that just reflects the reality of like how the sport's changing. Back in the day, there was less care about cost, about less green energy, less waste. So they would run parts to failure. So you saw a lot more failure. Where now there's a lot more focus on ensuring that you can not fail, so you can actually finish the race. Quick one on looking at contingency coefficients in Spearman row by the different seasons, individual seasons. What really stands out is the overall predictive strength that qualifying holds. You see it more in the contingency coefficient in the blue, where the Spearman row kind of is all over the place, but it's still pretty strong with the worst at 0.65. What's also interesting, the 2 years that are the lowest spikes are the last year of a regulation change, which kind of may reflect just experimentation. We're actually seeing that a little bit this year, because this is the last year of a regulation set, so there's more willingness to use, say, rookie drivers, where they're more likely to take failures. Where next year they want drivers that are, steady in the sport and have some experience. Another thing I did was using ordinal logistic regression. Because this data was all ordinal data, we cared about positions, 1, 2, 3. We don't care about the distance between 1, 2, and 3. Finishing second is not twice as bad as finishing first. We just use an OLR instead of a linear regression. Again, easy to do in Python. The stats model has the ordered model function, so it's easy to throw this in. Using, again, the same predictors, qualification, 3 practice sessions, trying to predict the final race outcome, centering and scaling the inputs, using the logic function of the BFGS optimizer. And the results from that was that, again, more or less hold the same. P-value is all less than 0.001. The coefficient beta value was strongest for qualification, almost 4 times larger than the next closest one, which was P3. And we standardize it, you get something similar. It's almost 4 times larger than P3, which again stands out that qualification is a really strong predictor of races, which goes back to original hypotheses that the fastest car on a Saturday is probably the fastest car on a Sunday. Looked at some threshold cutoffs within the OLR. Big highlights to take away from this. So what this is it's where the model looks at the cutoff points between 2 transitions in ranks. So looking like 3, 4 threshold would be the odds of finishing 3 and above versus 4 and below. And what you see is it's really contentious in the top 1, 2, 3, 4 positions. Everyone's trying to get on the podium. The middle is a lot more flattened out. And yeah, model fitness we can talk about after if you're interested in. Big takeaway from this is that qualification is a strong predictor of success. P3 is good. OLR is useful. Was able to improve on the original results using more data and more approaches. So quick, what's next? There is a race weekend this week. So when I started this session, the qualification was red flagged, but practice this morning suggests that Oscar Piastri and Lando Norris, McLaren 1-2, they're probably going to finish first in qualification. I'll see what that looks like when I finish this talk. And they'll probably win tomorrow. Yeah. The qualification session was red flagged this morning, so I wasn't able to see it before I started talking. And wrapping it up, if you want to get involved, come chat with me.